Okay, let's unpack this. The universe, I mean, where did it all come from? For a long time, the Big Bang has been the dominant idea, right? The
Mm.
single colossal explosion that started
Let's just
everything.
get your picture, yeah.
But what if there's another way to think about it? What if the universe actually grew through a series of like rapid, invisible bursts? It's a pretty mind-bending concept, honestly.
It really is.
And that's exactly what we're going to explore in this deep dive.
What's really fascinating here is this shift, um, moving away from just a one-time event to potentially recurring process.
Mm-hmm.
And that has huge implications for how we understand the universe's history and, well, what's driving it all.
Exactly. So we're diving into this really intriguing new theory centered around these temporal singularities. You can think of them as sudden, incredibly powerful jolts in time that ripple across the entire cosmos.
Right. Not just in one place, but everywhere.
Yeah, and this idea could completely change how we see galaxy formation, even the accelerating expansion of the universe.
Mm.
And get this, it offers a potential explanation without relying on those mysterious concepts, dark matter and dark energy.
Which is huge.
It really is. I mean,
Yeah.
this isn't just a small tweak to our understanding. It challenges the very makeup of the cosmos we usually imagine. It could put decades of research into those elusive things in a totally new light.
Yeah, and if you think about the bigger picture, the whole enigma of dark matter and dark energy, it's been such a major puzzle in cosmology for, what, decades now?
Oh, absolutely.
So this new model presents a potentially elegant alternative,
Hmm.
which is why it's generating so much excitement among people trying to figure out these fundamental questions.
Our guide through this cosmic rethink is Dr. Richard Lieu. He's at the University of Alabama in Huntsville. His recent paper in classical and quantum gravity, that's our main source here. So our mission today is pretty straightforward. Let's try and get our heads around the core of this new model and figure out why it's creating such a buzz in the scientific community.
Okay, so let's start with the central idea then, these temporal singularities. How does Dr. Liu actually picture these events shaping the history of the cosmos?
Right. So think of it this way. Instead of just one enormous bang, imagine a sequence of incredibly fast, super powerful spikes in time. These are the temporal singularities, and they spread throughout all of space.
A sequence, not just one.
Exactly. Dr. Liu suggests cosmic history isn't just that single event, but it's a series of these energy boosts. Each one floods the universe with matter and energy, essentially giving it a sudden growth spurt,
Yeah.
pushing the expansion and setting the stage for the massive structures we see, like galaxies and clusters. He even argues his model can explain both how those structures formed and the overall expansion we observe today.
And the key aspect here, you mentioned it, is that these bursts uniformly affect all space. That's a really crucial point, isn't
That
it?
really is.
Because it offers a potential way to explain things we usually attribute to, well, the uneven clumps of dark matter or the pervasive push of dark energy, if it happens everywhere at once.
It changes the requirements, and this isn't a completely new line of thought for Dr. Liu either. He actually touched on similar concepts in his work back in 2024.
Ah, right. I remember that.
Yeah, where he's explored the possibility of gravity working without needing mass. That idea alone got a lot of attention, apparently over 41,000 reads.
Wow.
And that earlier work also aimed to explain why galaxies hold together without needing dark matter, trying to solve the same puzzle.
But there was a bit of a challenge with that earlier model, wasn't there? Something about negative density.
Exactly, you nailed it. While mathematically it kind of made the model work, negative density is a really tough concept to picture physically. Like, what is that?
Yeah, it's hard to wrap your head around.
The truly exciting thing about this new model that we're talking about now is that it gets rid of that negative density idea completely. But it still achieves those same results, explaining galaxy cohesion, and, he argues, even explains more about the universe's expansion, all without the negative density.
That's a significant step forward then.
Mm-hmm.
So these temporal singularities themselves,
Yeah.
what are they actually like? When we say singularity, what are we picturing here? Is it like a black hole?
Good question. Not necessarily like the point of infinite density we imagine in a black hole. Think of it more as an incredibly localized and intense event in time, a rapid burst that has profound effects on space-time itself.
An event in time, not just space.
Right. And these events are incredibly fast, like faster than you can blink, probably. And they happen very rarely across the vastness of space and time. That's why, Liu says, we can't currently detect them with our instruments.
Ah, okay. Too fast, too rare.
But their impact is huge. Similar to the Big Bang, they bring matter and energy into existence. However, and this is really important, they do it without breaking the known laws of physics.
That's a key difference from some older ideas, isn't it? Like Sir Fred Hoyle's steady-state universe.
Exactly, you're thinking along the right lines. That model tried to explain continuous creation of matter, but it ran into the basic problem of violating the conservation of mass energy, a big no-no in physics.
Right, matter just appearing from nowhere consistently.
Yeah, Hoyle suggested matter was just constantly popping into existence as the universe expanded. Lieu's model is different. He's saying matter and energy appear and disappear suddenly during these bursts, but always in a way that respects the fundamental rules.
So the books still balance, so to speak.
Precisely. There's no violation of conservation laws. And the fact that these singularities are unobservable because they're so rare and quick, Lieu actually suggests that might make the model more realistic, not less.
Interesting perspective. Okay, now let's tackle the other big mystery.
Yeah.
The accelerating expansion of the universe. Usually that's where dark energy comes in. How does Lieu's model account for this?
This is where the idea of negative pressure comes into play. Now, usually we think of pressure pushing inwards, right? Like air in a balloon.
Sure, standard pressure.
But negative pressure in space is, well, it's weird. It actually pushes outwards. So it acts like an anti-gravity force, almost.
An outward push.
Yeah.
Okay, I can see how that would drive acceleration.
Yeah. It's a perfect candidate to explain why the universe's expansion is speeding up. Lieu uses an analogy with a magnetic field to help visualize it. He talks about the negative pressure that exists along a magnetic field line.
That's a helpful analogy, actually. Sort of a tension pulling outwards along the line.
It is, and it's interesting to remember this isn't totally out of left field. Even Einstein, way back in 1917 with his cosmological constant, he considered negative pressure as a way to stop the universe collapsing under its own gravity. So the concept has been around, even if it wasn't fully developed then.
Right, it has historical precedent. And in Lieu's model, it's the pairing of this positive mass energy, the stuff created in the bursts, with this negative pressure that drives the expansion.
Exactly, that's the engine. And crucially, it does this without needing to bring back that problematic negative density idea from his earlier work.
Gotcha. So positive energy, negative pressure, they work together.
Right. And this balance, he argues, also helps explain the stability of the universe's structure. These singularities aren't just creating matter and pushing expansion, they're also setting the stage for galaxies to form and hold together.
The job we usually give to dark matter.
Precisely. But in Lieu's view, maybe no dark matter needed for that either. The structure arises naturally from these events.
Okay, this is really starting to sound like a unified picture. Which brings us back to the title of Dr. Lieu's paper. Are dark matter and dark energy omnipresent? What's his main argument there? What's the answer?
Well, his answer is basically no. He believes dark matter and dark energy aren't these constant, ever-present components filling the universe all the time. Instead, he proposes they only appear, or their effects manifest, in these brief, fleeting moments during the rapid bursts when matter and energy uniformly fill all of space.
Only during the bursts themselves?
Yeah. In between these bursts, they simply don't exist, or at least their effects aren't needed to explain what we see.
So there's a similarity with the standard Big Bang model. You still have a cosmic burst, but the crucial difference is this idea of them happening repeatedly.
That's the core difference. The Big Bang is generally seen as a one-time event in the standard model. Lieu is suggesting these are recurring events, like pulses.
Okay.
These repeated bursts could potentially explain both the initial creation and the ongoing expansion and evolution. Each pulse distributes matter, which then clumps together because of regular gravity, forming galaxies, clusters, the cosmic web we see.
And the fact that these events are so short-lived.
That, Lieu suggests, might be the very reason we've never directly observed dark matter or dark energy. Maybe we've been looking for something that's always there when its effects are actually episodic.
That's a fascinating thought. If they're not always there, you wouldn't expect to find a stable particle just floating around.
Exactly. It shifts the search, potentially.
Which naturally leads to the big question. How on earth could we possibly test such a theory if these bursts are so fast and rare and undetectable?
It definitely sounds like a challenge, doesn't it? But Lieu suggests we might find evidence not necessarily by building, even bigger space telescopes to look further out, but by taking a really, really close look at the data we already have from powerful ground-based telescopes. He mentions specifically Keck Observatory, the Isaac Newton group of telescopes, places like that.
existing data. How?
Well, the key is in how these telescopes collect information. They observe the light from distant galaxies across a huge range of redshifts, right?
Right. Redshift tells us how fast things are moving away from us, basically how stretched the light is, like the Doppler effect for light.
Exactly like the Doppler effect. The further away, generally the faster it's moving, the higher the redshift.
Okay.
So Lieu proposes redshift slicing the data. Imagine taking all that data on galaxy distances and speeds and slicing it into incredibly fine layers based on redshift.
Like super thin time slices almost.
Kind of, yeah. By doing this, astronomers could potentially look for sudden jumps in the apparent distance or recession velocity of galaxies at specific redshifts.
Jumps, not smooth changes.
Exactly. These jumps, if they were detected, could be the telltale signs of past singularities, evidence that the universe didn't just expand smoothly, but grew in these pulses.
Ah, I see. So you'd expect a smooth curve in the standard model, but here you might see steps.
That's the idea. He even puts it quite directly in the paper, something like, given sufficient redshift resolution affected by the redshift slicing, one might just find that the Hubble diagram exhibits jumps.
Wow. Okay, that's a concrete prediction. That's testable, at least in principle.
It is. It would require very careful analysis of large data sets, but it's a potential observational signature. So for now, it's crucial we remember this is still a theory, right?
Of course. Needs verification.
But it's one that, if borne out, could fundamentally change how we understand dark matter and dark energy. Maybe instead of searching for invisible particles or mysterious energy fields.
We should be listening for the echoes.
Yeah, listening for the echoes of ancient, unstoppable births as like a completely new way to understand how the universe works.
So just to recap for everyone listening, we've really dug into this idea of temporal singularities, these sudden universe-wide bursts in time and energy that Dr. Lieu is proposing. And the core idea is that these bursts, happening repeatedly, could be the engine driving the universe's origin, its expansion, and even the formation of structures like galaxies.
And the most, I guess, striking implication, the thing that really grabs you, is the potential to explain all this cosmic machinery without needing to invoke dark matter and dark energy, these things that have puzzled us for so long.
It really does turn things on their head,
Huh.
which leads to a really interesting question for you listening in. If the universe's history isn't this smooth, continuous expansion from a single point, but instead it's built on a series of these rapid, powerful steps, what other hidden rhythms might we be missing?
Yeah, it makes you wonder, doesn't it? Is the universe's story far more dynamic, maybe more pulsed, less uniform than we've previously imagined, with these bursts being fundamental but unseen events shaping everything?
A different kind of cosmic heartbeat.
Exactly. We really hope this deep dive has given you a fascinating new perspective on some of these huge questions about our universe. It's certainly given me a lot to think about.
Me too. It's a compelling alternative picture.
So if you enjoyed this exploration into, well, the frontiers of cosmology, and you want to stay on top of future deep dives into the latest ideas,
Then definitely hit that like button and subscribe.
yeah, please do. It helps us keep bringing these kinds of discussions to you. Thanks for joining us.